Assalamualaikum and good evening everyone. My name is ECH3120 and my matrix number is 196811.
My name is Nuraini Rushada binti Mama Azhar and my matrix number is 198558.
Hello, my name is Nur Amir Izzati binti Muhammad Hairul Effendi. My matric number is 198787.
My name is Kuratu Aini binti Firdaus. My matric number is 199804.
Assalamualaikum. My name is Nurjana binti Muhammad Shukri and my matric number is 198968. So my group and I are going to present about solid-solid equilibrium, and I'm going to present about what is solid-solid equilibrium and the condition for solid-solid equilibrium. So what is solid-solid equilibrium? So the solid-solid equilibrium is the solid-solid transition that are transit between different crystalline forms, also known as polymorphs of the same compound, for example, pure crystal A and pure crystal B. From the thermodynamic standpoint, solid-solid transition can be characterized by the temperature at which two crystalline phases can coexist in equilibrium. Solid-solid equilibrium phase region is existing under eutectic point in solid-liquid equilibrium phases diagram. So this is the figure 1, which is the solid-liquid equilibrium phase diagram. And this is the region for solid A plus liquid, and this is the region for solid B plus liquid. This is the solid-solid equilibrium phases for pure liquid, pure solid A and B. So this is the eutectic point. Eutectic point is reached at the point E when all the three phases, for example, crystal A, crystal B, liquid, all exist in the equilibrium. So when this point is reached, the temperature must remain constant until one of the phases disappear. So the horizontal line is known as the solidus, while this two line is known as the liquidus. 198968. So next, I will explain about the condition for solid-solid equilibrium. For inviscid fluids, the equilibrium condition are continuity of temperature, continuity of velocity, continuity of pressure, and continuity of generalized specific Gibbs energy. However, the main concern arises when the stress tensor is not simply a pressure. Underlying physical principle are the conservation laws of and the entropy inequality. For solid, these principles are needed for derivation of generalization of specific Gibbs free energy. The derivation is necessary and sufficient to conserve mass, momentum, and energy to satisfy the entropy inequality. The needed condition must be material-specific constitute relation. This is the reference, and all the information above is from the research I have made from website from Dr. Stephen A. Nelson of the Tulane University, while for the solid-solid phase transition information is from the academic journal from Science Direct website. So that's all from me. Thank you.
Next is how solid-solid equilibrium form from the solid-liquid equilibrium phase diagram. So from the figure 3 here, we can conclude into several points, which are the first one, at temperature of T1, which is temperature 1, a solid A is start to form. By further lowering of the temperature, will cause a small solid A to form, which means if we move from temperature 1 to temperature 2, this will increase the form of the solid A. The liquid composition is changed from point 1 to point 2 to point 3 and to point E. Point E is known as the eutectic point. Eutectic point is a point on a phase diagram where the maximum number of allowable phases are in equilibrium. When this point is reached, the temperature must remain constant until one of the phases is disappear. A eutectic is an invariant point. In the region between temperature 1 and temperature eutectic, two phases will present in the system, which is the solid liquid and the solid A. At the temperature of eutectic, solid B will start to form and three phases will coexist. The phases are liquid phase, crystal of A phase, and also crystal of B phase. At this point, the temperature must remain at T greater T until one of the phases disappear. When the liquid crystallizes completely, only pure solid of A and pure solid of B will remain. A mixture of these two solid phases will be in the proportions of the original mixture. Next is mole of composition. The rules for mole of composition is in equilibrium crystallization, the final composition of the system will be identical to the initial composition of the system. To observe how much of each phase is present when we stop the crystallization process, for the percentage of solid A, we can calculate by using B divided by A plus B times by 100. And for percentage of solid B is 100% minus percentage of solid A, which we calculated earlier. And for the percentage of liquid, we can calculate by using A divided by A plus B times by 100.
Okay, so for the binary system and new compound phase diagram, figure 5 shows the binary system or the typical phase diagram. Only solid of pure A and pure B are stable to form solid. So based on this phase diagram, we can see there are three two-phase region, which is solid A and B, solid A and liquid, and solid B and liquid. So the two compound A and B will react and form a third chemical compound, which is C. So if compound C is stable in liquid phase, which means it does not decompose by melting, the phase diagram will look like in figure 6. So reaction that form compound C is 2A plus B will form C, and the formula compound of C is A2B. So based on figure 6, there are 5 two-phase region, which the first one is solid B and liquid, solid A to B and B, solid A to B and liquid, solid A and A to B, and last one is solid A and liquid. When solid liquid equilibrium exists, two types of three phase are in equilibrium, which the first one is solid A in solid state and A to B in liquid state, and the second one is solid B in solid state and A to B in liquid state. Many binary mixture form more than two compounds. Therefore, it will further the linkage of eutectic diagram, which allowed for their phase diagram. The application of solid-solid equilibrium is the first one, predicting the absorptions of arsenic, and for multi-layer adsorption, which is similar to bad isotherm. Bad isotherm is the explanation on the physical absorptions of gas molecules on a solid surface. Okay, a bad isotherm is important as analysis technique for measurement of specific surface of a material. It is usually used for probing gases that do not chemically react with material surface as an adsorbate to quantify the specific surface area, for example nitrogen. So these three scientists make a few assumptions based on the multi-layer adsorption. The first assumption is, imagine there are a few molecules arranged together, and one side absorptions of a molecule does not affect neighbor side absorption. Second assumption is, usually the molecule will arrange and stack in layers, and a molecule can act as a single absorption site for molecule of the upper layer. The third assumption, the uppermost molecule layer is in equilibrium with the gas phase. And lastly, the desorption is a kinetically limited process.
Now, I'm going to explain the example of SSC, which is on the phase diagrams of allotropes and polymorph. Elements such as ferrum and compound zirconium oxide can actually exist in more than one crystal form. So, how does this example related to the solid-solid equilibrium? I'm going to explain in details based on the phase diagram shown in figures A and B. The alpha, gamma, and delta values of ferrum are shown in figure A. The gamma phase is face-centered cubic FCC, while the alpha and delta phases are body-centered cubic BCC. The FCC phase has the highest packing density, which makes the gamma phase has the highest density and lowest molar volume, and vice versa. During the transformation of alpha ferrum, the delta V is negative, and based on the Clapeyron equation, the negative slope dP over dt of the phase boundary between alpha and the gamma phases. Meanwhile, in figure B for zirconia, we can see two anomalous slopes, one between the monoclinic and tetragonal phase, and one between the tetragonal and cubic phase. The reason for these different phases is related to the density increase in respect to the volume reduction from the monoclinic by the tetragonal and to the cubic phase. Such rearrangement of crystal lattice needs time. For example, fast changes of the temperature of different metastable behavior. You can read this in details in the next slide. Figure above shows the crystal structure of zirconia increase in density when the temperature increase. This is an example of an anomalous behavior.
So for the last one, I will explain on the microstructure of the eutectic phase diagram. So as you can see in the diagram, there are two lines which indicate two reactions. So first, we will observe the reaction of A. At the higher temperature, the microstructure in the liquid phase. As we go down, we can see crystal A is formed in the liquid. When the temperature is decreased, more crystal A is formed and the liquid is disappeared. So for reaction B, it is quite the same like reaction A, but instead of forming crystal A, it forms crystal B. Now we will see the microstructure on the reaction C. Reaction C starts at the liquid. So when it reaches at the eutectic point, which labeled as E, crystal A and B will form, and all phases including liquid is in equilibrium at this point. When the temperature is decreased, they will grow in one direction because of the resistance by the adjacent crystal. When they grow in one direction, they will form layers. More layers is formed in granules because they grow in different direction. For reaction D, the microstructure will always start as liquid at higher temperature, and then by lowering the temperature, crystal A will form in the liquid plus alpha phase. Further lowering the temperature, the solid A will grow larger. After passing the eutectic point, the former crystal A will grow completely, and the new crystal A and B will form layers around it. The former crystal A that grows completely is called pro-eutectic A, while the solid A that forms layers is called eutectic A. The reaction is same goes by to reaction E, but instead of forming crystal A in the liquid plus beta phase, it will form crystal B. And the former crystal B that forms in the liquid plus beta phase that grows completely is called pro-eutectic B, and the solid B that form layers around it is called eutectic B.